So this, hi everybody, is lecture 25. We're discussing section 8.5, again, power series. This is the second day of that. We started on Monday. So, I want to do, so recall, Monday we talked about power series, and we had them centered at 0. All of our examples looked like this. And I think you, in your recitation, also had power series that look like this. So this is C0 plus C1x plus C2x squared, and so forth. Today, we're going to be looking at power series centered at A. And that looks like this. The same summation symbol from 0 to infinity of Cn, but instead of just x to the n, we have x minus a raised to the nth power. So that's going to be C0 plus C1 x minus a plus C2 x minus a squared, and so forth. That's one thing I wanted to talk about. Another thing that I want to do is I want to review some stuff involving factorial, and I'm going to do it on the sideboard, so follow me over here. So meeting part 1. Is to review, discuss expressions involving factorial. So remember that n factorial means this. N times n minus 1 times n minus 2, all the way down to 2 and 1. And so n plus 1 factorial would be the same idea, n plus 1 times n minus 1, all the way down to 2 times 1. But recognize that in this expression, this much of it is just n factorial. So n plus 1 factorial equals just n plus 1 times n factorial. So n plus 1 factorial over n factorial is just the expression n plus 1, no factorial. That's easy enough. Let's get crazy. Let's consider this. Kn factorial. Okay, well that's going to be a messy thing. I don't know what k is, where k is a positive integer. Could be 5, could be 17, could be a billion, whatever. This is going to be Kn, whatever that is, Kn minus 1, all the way down to 2 and 1. You just always do the same thing. Now, let's look at this. Kn plus k times the quantity n plus 1, and then that thing, so let me make this bigger for the studio audience. No, for the Academy Awards. It's got to be big. K times the quantity n plus 1. That whole thing factorial. Well, let's make the thing inside look a little bit simpler. So this is going to be kn plus k inside, and that's going to be factorialed. Well, that just means we're going to do the usual thing. We're going to start with that term, kn plus k, and then we're going to subtract 1, so we're going to have kn plus k minus 1. We're going to have k, and then we're going to go all the way down to, keep going. And at some point, well, I'm going to do another term. This is going to be kn plus k minus 2. And at some point, this number is going to grow so big that it's going to be almost as big as k. So kn plus 1. And then we're going to keep going, kn. And we're going to go kn minus 1 all the way down to 2 and 1. So again, this is a messy thing, really messy. But when you break it up, you realize you're going to have this big product of all these terms, and midway there's going to be this thing going on. There's going to be a transition where you've got this, and realize that from here on, this stuff is kn factorial. So I'm going to call this, well, I'm going to call this stuff. And this stuff here is k in parentheses, all n factorial. So this thing is stuff times kn factorial. Well, where am I going with this? That means that suppose I have this and I divide by this. So in this case, I developed this because this is going to turn up in one of our examples today. What's going to turn up in our examples also today is going to be this ratio, kn factorial divided by k times n plus 1 factorial. Okay, so that's going to be kn factorial, and on the bottom I'm going to have stuff times kn factorial. This thing, k times n plus 1, that whole thing factorial equals that stuff times kn factorial. So realize the kn factorials cancel, and I just get 1 over stuff. So stuff, again, is this. This doesn't seem like I'm doing you any favors. This is really messy. But you know, this is way better than the bigger mess that we have if you write all this out. So a bunch of stuff does cancel. It doesn't look as nice as this cancellation, but it is a cancellation that helps all the same. So that's meeting part 1, is just reviewing stuff involving factorials. So meeting part 2, how many of you have a organic chem exam today? All right, previous section, a bunch of people were running off to organic chem. So meeting part 2 is examples. And it's going to be examples of series centered at A. So centered at A makes them a little bit harder than what we did on Monday and a little bit harder than what you did in recitation. And also, they're just harder. So if you ask the people who are in the organic chem test right now, they're probably thinking, organic chem is really hard, but it's not as hard as what we just did in calculus. So here we go. So example 1. Find R and I for the series summation from 1 to infinity of n over b to the n times x minus a to the n. All right, who can help me out here? Raise your hand if you know what I'm referring to when I say R, and what am I referring to when I say I? Cassidy? Yeah, radius of convergence and interval of convergence. The radius of convergence and the interval of convergence. So notice, again, this is a series centered at A. Now, what's hard about this is it's a series centered at A, and also there are no numbers in here. It's just letters. Well, as we did on Monday, let's do the ratio test. So the limit as n goes to infinity of the absolute value of the ratio, a n plus 1 over a n. That a is not the same as this. This is just some number a. This is the thing which stands for the terms inside the summation. So this is the limit as n goes to infinity. I'm going to have on the bottom that whole thing, n x minus a to the n over b to the n. And on the top, I'm going to have the same thing, but with n plus 1. And as I did on Monday, I hate fractions over fractions, so I'm going to rewrite this with a single baseline. And so keep in mind, I'd like to stop doing this step. We always know it's going to be this divided by this, and we're going to have to rewrite things with a single baseline. So I'm going to do that now. And I'm going to stack things so that things that cancel or things that are going to cancel are going to be stacked above each other. So let's see. In the top, I'm going to have an n plus 1. In the bottom, I'm going to have an n. I'm going to stack those above each other. And then in the bottom, I'm going to have a b to the n plus 1. And on top, I'm going to have a b to the n, because when I flip this over and multiply, I'm going to have a b to the n on top. And then on top, I'm going to have x minus a to the n plus 1 over x minus a to the n. So again, what I did here is I rewrote this with a single baseline. And I'm going to say like factors stacked. Because it's going to be helpful when we think about canceling them. So what I would like to do in the future is to go directly from here to here, because we always know we're going to be doing this. So don't be shocked in the future examples if I skip this step and we're just going to pick out these terms. All right, so raise your hand if you can tell me some cancellation that I can do here. Go. Ian?
The x minus a's to the n.
So what am I going to be left with?
X minus a in the numerator.
Okay, somebody else. Can somebody else tell me something I can cancel? Good. All right, now, raise your hand if you can tell me what I can do now. Kenzie?
You plot the x minus a over b.
So the x minus a over b does not depend on n. So it seems like we can pull it out. But it turns out that that's not given. It's not automatic that we can pull it out. It sure seems like we can do it. When I do that, I end up with an absolute value over the x's, around the x minus a. And then I have this limit as n goes to infinity of n plus 1 over n. And I don't need absolute values because n is a positive number. Now, again, what's my problem? Why am I obsessing over this? Why is there a question mark here? Well, because this is only legal if this limit turns out to be a number. So that was it's one of the basic rules of limits. You can pull out constants that don't depend on the variable if the limit turns out to be to exist. Other things you can do with limits. You can break limits of sums into sums of limits if those independent limits exist. So you can do all these things with a question mark, but we got to check. Can somebody tell me what they think this limit's going to be? Silver?
1.
Yeah, this is the number 1. There are a couple of ways you can do this. This is the limit of n over n plus 1 over n. 1 over n gets closer and closer to 0, so this is just the limit of 1 plus 1 over n. That's getting closer and closer to 1. Or you could do L'Hopital's rule or whatever. Okay, so since this limit does exist and it's a number, we're okay. It was okay to pull out those constants. So this is just x minus a, absolute value, over b. So that limit of that ratio is that. So since the limit test, or the ratio test, says the series converges only when the limit is less than 1. So this thing has to be less than 1. We must have absolute value of x minus a over b is less than 1. So that tells us that x minus a is less than b. At this point, have we got anything useful? Go back to our question. Our question was find r and find I.
Radius of convergence or speed?
Yeah. So remember what the radius of convergence is. Remember that, go back to these power series. A power series centered at A. Let me go back to this. You have this in your notes. This, you don't need to write this down because it's already in your notes, but this is C0 plus C1 x minus a plus C2 x minus a squared plus. Now, when x equals a, all these terms become 0, and the whole series just equals C0. So for sure, the series converges when x equals the number a. The question is, how far away can x get from a and have the series still converge? That's the idea of the radius of convergence. So this is telling us how far x can get from a. The distance x can wander away from the number a is b. So this tells us the radius of convergence is the number b. So we've done part of our problem. Now, what about the interval of convergence? The interval of convergence I, it could be, well, it could be just from there to there without the endpoints. You know, that's, or it could be that the left endpoint's included, but the right endpoint's not. Or it could be that the left endpoint is not included, but the right endpoint is. This should be a plus b. I'm going to erase this. And the last possibility for the interval of convergence, it could be that both endpoints are included, a minus b all the way to a plus b, including both endpoints. The only way to know is to actually check the endpoints independently. So test the convergence at the left endpoint. That is when x equals a minus b. That's how far x has wandered from the number a. So let's go back to the series. Well, the series was, remember, the sum from n equals 1 to infinity of n over b to the n. And then in top, I've got x minus a. So that's going to be a minus b. That's the value of x minus a. And that's all raised to the n power. OK, a minus b minus a. That's going to be minus b. So I have n times minus b to the n over b to the n. Now, this has come up, this was spooking a lot of you. There's some really easy cancellation here. But if you don't see it, then take baby steps. That's the thing. So I'm going to write this as the summation as n times minus 1 times b. Okay, that's a baby step. B is the same as minus 1 times b. And then, but minus 1 times b all raised to the n power, that's the summation of minus 1 to the n times b to the n over b to the n. Now, can anybody spot anything that can cancel or simplify here? Carson, Chase.
B to the n.
Yeah, the b to the n. So I end up with the summation from 1 to infinity of n times minus 1 to the n. So a lot of students can't get from here to here. They'll stare at this and they don't know what to do. So again, take baby steps. Minus something to the n power is the same as minus 1 to the n times that thing without the minus sign to the n. Okay, so here's a series. Does this series converge? So the question is, again, we're still in example 1. Does this series, n equals 1 to infinity of n times minus 1 to the n. Now, what does that look like? That's minus 1 plus 2 minus 3 plus 4. Does that converge? Who can answer that question? Liam?
No,
You're right. Why not?
it's alternating, but it's not decreasing.
Right. So remember the test for divergence says if the limit of the terms is not 0, then the series diverges. By the test for divergence. Since the limit of these terms as n goes to infinity, the limit of n minus 1 to the n, since that's not 0, the series diverges. So what were we doing here? We were testing to see if the number x, so go back over to here. We had all these possibilities for the interval of convergence. And what we've just found out is at the left endpoint, the series does not converge. So the left endpoint is not in the interval of convergence. So we're looking at either this possibility or this possibility. So our conclusion here is that the number x minus x equals x equals a minus b is not in the interval of convergence. All right, now let's test the other endpoint. X equals a plus b to see if it's in the interval of convergence. So the series becomes this. The sum as n goes from 1 to infinity of n over b times a plus b minus b, or a plus b minus a to the nth power. So the a's get together and have an a party. Oh, and this should be over b to the n. So this is the sum as n goes from 1 to infinity of n times b to the n over b to the n. And that's the sum as n goes from 1 to infinity of n. So that's 1 plus 2 plus 3 plus, and that diverges. So the conclusion is that that number is also not in the interval. I would suggest when you write up problems, don't just sit at WebAssign and do homework, but actually write stuff down. Write down stuff like this. Write down what you're doing. Write down what you're testing so that you are clear with yourself what you're doing and you're clear with the reader what you're doing. So the conclusion is the interval of convergence is I, and it goes from a minus b without the endpoint to a plus b without the endpoint. Again, of all those four possibilities, I'm sorry, we already had that the radius of convergence was b, and we got now that the interval of convergence is that. That's the end of example 1. All right. So end of example. Example 2. So find R and I for the series sum from 1 to infinity of n factorial times 2n minus 1 to the 2x minus 1 to the nth power. Does anybody notice something that's kind of annoying about this one? Well, what's annoying to me is it's not in standard form. Standard form is that. X minus a to the nth. I don't have that. I have 2x minus 1 to the nth. So I want to put our series in standard form. So our series S is n factorial, and I'm going to factor out a 2. 2 times x minus 1/2. That whole thing to the nth power. And then I can bring out the 2 to the nth. So this is the sum as n goes from 1 to infinity of n factorial 2 to the nth times x minus 1/2 to the nth power. So there you see that if you look at this, you might think, oh, the value of a is the number 1, but it's not. The value of a is the number 1/2. So the question is, when does this thing converge? Well, clearly not clearly, but just remember, when x equals a, then all of these terms, when x equals 1/2, all these terms become 0 except the very first one. So the series definitely converges when x equals 1/2. So the question about the radius of convergence is, can x wander away from that and still have the series converge? So let's do the limit test, or the ratio test, to find R. So the limit as n goes to infinity of absolute value of a to the n plus 1 over a to the, or a sub n plus 1 over a sub n. So this is the limit as n goes to infinity of, I got a, on top, n plus 1 factorial 2 to the n plus 1 times x minus 1/2 to the n plus 1. And on bottom, n factorial 2 to the n, x minus 1/2 to the n. Okay, here we get to use that fact about factorials from the sideboard. N plus 1 factorial divided by n factorial is just the number n. Yeah. Was there a comment? Oh. So I just have absolute value of n plus 1. 2 to the n plus 1 over 2 to the n is just the number 2. And then x minus 1/2. Now, who has an idea of something we can do here? And I'll just say remember what my wife always said to the cat, don't do a bad thing. So, who has an idea of what we can do here? Yeah, Marcy?
We could take 2 quantity x minus 1/2 out in front of the limit.
That's the bad thing. That's what everybody says. This is why, remember what I said about the boring rules of limits? Here's a case where the chickens come home to roost, or whatever. What comes home to roost? Is it the cow? Well, the cows don't roost. So let me get out my blood chalk. So let's go over to the sideboard. Can we pull out the 2 times the x minus 1/2? So over here on the sideboard, so I guess writing in red is obnoxious. So I'm just going to ask this question. Can we pull out the 2 in the x minus 1/2? So, so the limit as n goes to infinity of n times 2 times x minus 1/2, that would be 2 times x minus 1/2 would have to be in absolute value signs times the limit as n goes to infinity of n plus 1. What's that limit? Say again? Yeah, this limit is infinity. So x minus 1/2 times infinity. Now what's that? You can't do arithmetic with infinity. You can't do algebra with infinity. So the answer to this question, can we pull that thing out? No, can't do it. We're not allowed to pull this thing out. So let's go back over to here. We're stuck with this thing being on the inside. So we're interested in what values of a, for what values of a does the series converge, for what values of x does the series converge? So the question is, when would this limit be a number that's less than 1? Well, you know, we already know that the series, the original series, converges when x equals 1/2. So that's one possibility. The other question is, what about some other values when x is not equal to 1/2? So let's consider this limit in 2 cases. One is that when x equals 1/2, of course, again, that's the known case. We know that the series is going to converge. But let's just go through it anyway, because it's fun to have something that we know. And then the other case is case 2, when x is not equal to 1/2. We're interested in are there any other x values for which this series converges? That's the question of finding the radius of convergence. So case 1 is when x does equal 1/2. So in that case, the limit becomes this. The limit as n goes to infinity of absolute value of n plus 1 times 2 times 1/2 minus 1/2. Oh, but 1/2 minus 1/2 is just 0. So this is the limit as n goes to infinity of n plus 1 times 2 times 0. And this is an honest multiplication. That's a number, that's a number, that's a number. I can multiply them. I just get the limit of 0. And what's that limit? That's 0. Good. That confirms that the limit does, so the series does converge. We already knew that. Now let's consider the harder case. Again, we're asking, are there any other x's where this series converges? Case 2 is when x is some value. We don't know what it is, but it's not 1/2. The limit becomes the limit as n goes to infinity of absolute value of n plus 1 times 2 times x minus 1/2. Okay, I don't know much here, but I do know that x is not 1/2. So this is not 0. And so this is not 0. So what's the limit? Marcy? Infinity. Doesn't matter what x is. If x is not 1/2, this thing is going to go crazy. So the series will not converge because the limit test, the ratio test says the limit has to be a number less than 1. So since the limit is infinity, the ratio test tells us that the series diverges. So what's my radius of convergence? In other words, how far can x get from the number from the number 1/2? Annika?
Can't go any farther than 1/2, it's just a general convergence of 1/2.
Right, so that means, so in this case, it's actually easier to answer the question about the interval of convergence first. The interval of convergence, that is the domain of the function, the domain of the series, is just the set that contains the single number 1/2. And so the radius of convergence, that is how far can x get away from 1/2? It can't. The radius is 0. That's example 2. Example 3. Find R and I for this series. The summation as n goes from 0 to infinity of n factorial. This is really bad. This is really bad. It's a really... Now, what's good about this is that it's a series centered at 0. Great. Okay, so we're going to use the limit test, use the ratio test to find R. In fact, in this problem, I'm just going to say find R. So we're going to do the limit as n goes to infinity of a sub n plus 1 divided by a sub n absolute value. Now remember what I said before. We know we're going to be stacking these things up, and we're going to want to stack like factors. So I'm going to put dot, dot, dot here. After I do that and I do my rearranging, I'm going to have this. I'm going to have a fraction with a single baseline. Okay, now on top, I'm going to have one of these babies with an n plus 1. So n plus 1 factorial, all to the kth power. And then on bottom, I'm going to have one of those just like that, but with just n factorial to the kth power. Okay, I'm going to have one of these with an n plus 1 on top. So x to the n plus 1, and then I'm going to have one of those with just an x to the n on bottom. And then I'm going to have one of these with an n plus 1 on bottom. And then one of these with an n on top. So again, that's after the various rearranging. All right, now this looks really bad, but notice both of these things are raised to the kth power. So I'm going to put those in parentheses. Limit as n goes to infinity. And I'm going to take those two factors and raise them together to the kth power. And what's on top is n plus 1 factorial, and what's on bottom is n factorial. Oh, that's cool. That's one of those things we know how to simplify. That's over there on the sideboard. X to the n plus 1 over x to the n, that's just x. And then this is on the sideboard. So kn factorial over k parentheses n plus 1 factorial is going to be 1 over stuff. That stuff is a big messy thing. And I don't want to write it here because I'm going to write it again over here. So this thing, remember when this is going to give us n plus 1 in the cancellation, but then that's inside of parentheses, so it's raised to the kth power. And then this is x. And then what have I got over here? I've got 1 over kn plus k, kn plus k minus 1, dot, dot, dot. And I'm writing down all this stuff. This keeps going all the way down to the number kn plus 2, and then finally kn plus 1. That's where that stuff, go over here to the sideboard, that stuff was this thing. So that's what's sitting there. So this looks terrible. But the thing is, this is a polynomial in the variable n. What's the degree of the polynomial? K. So this is a polynomial whose highest power term is n to the k. And then it's some other terms as well. So what I've got here is limit as n goes to infinity, and I'm going to put the x in front. And then I've got n to the k plus lower power terms. Now look what's on the bottom. How many factors do I have? I've got 1, 2, all the way up to k. I've got k factors sitting side by side. And each one of those factors has a kn in it. So this is a polynomial in n as well. And so this is going to have its highest power term is going to be nk to the kth power plus lower power terms. It's just going to be a big, ugly polynomial, and I don't even want to contemplate how ugly it is, because it's really ugly. But the thing is, when you take the limit of something like this, the lower power terms don't matter. So I can just ignore them. So this is the limit as n goes to infinity of x times n to the k over nk to the k. Isn't that beautiful? And notice that everything's raised to the kth power, so let's let's put parentheses around it. So this is the limit as n goes to infinity of absolute value of x. And then I'm going to have n over kn. That's all raised to the kth power. Now look, I can cancel. N over kn is just 1 over k. One over k to the kth power. So in other words, the limit as n goes to infinity of x over k to the k. Isn't that amazing? So we want this ratio to be less than 1 for the series to converge. We need the ratio to be less than 1. So we need x, absolute value of x, over k to the k has to be less than 1. So absolute value of x has to be less than k to the k. That's our radius of convergence. R equals k to the k. Hard example. I had a fourth example. I didn't get to it last hour either, so that's it. I'm going to hand back your quizzes.